Andreas, and with my group of Sama, Arapti, and Haewon Kang, we will be talking about pacemakers and the electrical properties of the heart. So quickly about what is a pacemaker. So it's a small device that is placed in the chest or abdomen to help control heart rhythms. And those heart rhythms are called arrhythmias. So that means that the heart is beating at an irregular pace. That can either mean too fast, too slow, or just irregular in its rhythm out. When we use physics, we are essentially using a low energy electrical pulses to prompt the heart to beat. So we're going to be replacing the irregular heart pulses with these electrical ones. And the way that we give these electrical pulses is through delivering them in a circuit in the heart.
Hi, I'm Helen Kang, and I'm going to be talking about the cardiac conduction system, or from here on out from the presentation, it'll be called the CCS. So a group of smooth muscle cells surround the heart, and they signal the heart to pump. And the mechanisms that allow an electrical signal to go through the heart and allow the contraction and the relaxation of the muscles include the SA node, the AV node, the bundle of His, bundle branches, and Purkinje's fibers. The SA node is known as our natural pacemaker, and it's like a node that's found in the right atrium. It sends an electrical signal over to the AV node, which is on the right side of the right atrium, and that allows for the contraction of the smooth muscles of the right atrium that pushes the incoming blood into the right ventricle. The pathway of the signal from the SA node to the ventricles, it's stimulated by action potentials. And as you can see, the SA node would be found right here in the right atrium, and then the AV node would be right here. The electrical signal from the SA node to the AV node would cause the contraction of the muscles right here and cause the blood that enters from the superior vena cava into the right atrium to be pushed into the right ventricle. This can be seen in an EKG or ECG as the P wave. And then the very large R wave would be seen as the right ventricle releasing the blood into the pulmonary artery, or having the ventricle muscles contracting hard enough to push it outside of the heart.
So multiple reasons as to why somebody would require a pacemaker would, as Ariana previously covered, be the misfiring in the cardiac conduction system. So this would include illness, such as in the SA node, which is basically our natural pacemaker. So obviously that would, be a threat to our heartbeat and our heart rate. And then there's also the heart block, which is just messing up in the electrical impulses in the heart, and sort of those messages not being transmitted correctly or being blocked in the atrium or in the atria. And then there's tachyarrhythmia, which is just one form of having an irregular heartbeat. Basically, tachyarrhythmia is going to be a speedy, kind of fluttery heartbeat, but any irregular heartbeat could be solved with a pacemaker. So the pacemaker is made out of electrodes and a pulse generator, and here in this diagram, as you can see, it's a really simple mechanism. So it has simply a battery and circuitry and a connector block within a case, and what comes out of that is the lead, which is the area that goes into the heart and which will send those electrical impulses. And this area will actually sit near the clavicle area, and the lead will actually go into the heart through the atria or the ventricles, depending on the kind of pacemaker that it is, which I will talk about later. And what the pacemaker can do is it's often mixed up with the defibrillator. So what the pacemaker does is it will solve for irregular heartbeats, but it actually can't restart the heart. So what it can do is just correct those electrical impulses and keep the pace steady and normal. Unlike a defibrillator, which can actually restart the heart in case it stops. So the pacemaker is good for, staying alive, but it's not going to resuscitate a patient. And this is just a basic diagram to show how the pacemaker is in the heart and where it's located. So as you can see here, there's the case which will sit right there underneath the clavicle, as I said previously, and this is where the electrical impulses will be generated from. And here, as you can see, the lead goes in through a major vein and will enter through the atrium and will sit right there in the ventricle. And as Helen previously showed in the anatomy of the heart, where the SA node is, it's going to sit in that vicinity, and it's going to generate those impulses. So the pacemaker, it can detect heart rate and your breathing rate, and it can, some advanced pacemakers can determine exactly how much oxygen you need, so that they can modify the electrical impulses in order to stimulate correctly. So it'll measure also the voltage of the heart. It's actually a sensor of sorts. So it doesn't just send those impulses, it also senses the body's conditions and senses the correct stimulation to send to the heart. So they're very sensitive, though, as the current and the voltage in the heart is really, really small and really minimal. So the pacemaker needs to be sensitive to those impulses and be able to interpret them. If it's not sensitive enough, it won't get a clear enough message from the heart, and it won't be able to do its job correctly. So, and because it's so sensitive, other devices can really easily interfere with the pacemaker's functions, and we will talk about that later in the presentation. So electrical noise will obviously interfere with the pacemaker's ability to send electrical impulses to the heart. So there's 3 types of pacemakers. There's single chamber pacemakers, dual chamber pacemakers, and biventricular pacemakers. So single chamber pacemakers are, as the name suggests, will go in through just one chamber of the heart. It's gonna enter either through the right atrium or the right ventricle, and it uses only one lead, which is obviously the little node that goes into the heart. And it'll obviously, monitor electrical activity to determine the kind of pacing that it's used, as most pacemakers do. For a dual chamber pacemaker, it'll deal with both the atrium and the ventricle, and it'll have 2 leads in there, and it'll help those 2 chambers kind of have a natural sequence as well. And here in the diagram, as you can see, there's 2 leads. There's one sitting right here in the atrium, and there's another one sitting in the ventricle. And for biventricular pacemakers, it's actually a type of therapy called CRT, which is cardiac resynchronization therapy. And another name for it is obviously biventricular pacing. And it's going to use a biventricular pacemaker, which is going to be different from the single or the dual chamber pacemakers. And it's going to kind of treat somebody who has like a delay in their heartbeat. And it'll sit in the ventricles, biventricular. And it's going to send really small electrical impulses because it's just a delay, right? And it can definitely improve somebody's quality of life if they have, really minimal heart problems. It's still a problem with electrical impulses in the heart, but it's just dealing with a delay in those ventricular contractions. And as you can see here, there's a biventricular pacemaker sitting underneath the clavicle, of course, and here you can see the lead sitting in this ventricle. And then right there, kind of like a dual chamber, it has 2 leads, but it also has, it actually has as many as are necessary for the function. There's actually 3 here. There's one right here in the ventricle. There's one sitting right there next to the atrium. And then there's another one right here next to the other atrium right there. And then finally, there's rate responsive pacing, which I kind of briefly mentioned as I was speaking, but it has to do with monitoring the body's movement, the body's oxygen, and determining whether or not the activity is, one that requires a lot of oxygen or a little bit of oxygen. And as you can see with this little graph here, depending on how much activity you're doing, the pacemaker will obviously sense the heart rate, and it'll be able to determine the kind of electrical impulses that are necessary in order to provide more oxygen, more blood, in order to make a stronger contraction. Just really quick here, what the slide is explaining is that it can be any kind of pacemaker because it's kind of an advancement in the abilities of a pacemaker, and that it can make it more effective and more efficient, so that it, instead of delivering the same kind of electrical impulses, it can adjust the kind of impulses that it sends depending on the kind of activity that you're doing throughout the day. So normally your heart obviously will speed up and slow down depending on what you're doing, you know, what kind of physiological processes are happening in your body. And obviously depending on the activity, it will, you know, increase or decrease. If you're, you know, exercising, running, walking, your heart rate's going to be, you know, higher than if you're just resting or sleeping or just sitting down. So a rate responsive pacemaker is going to respond to the rate of your heart, as the name would suggest, and it will basically change the kind of impulse that it sends, you know, either stronger or weaker, so that your heart can contract correctly, and it can provide the amount of oxygen that you need for whatever you're doing, and it's obviously more effective, and most pacemakers today have that kind of feature.
Pacemaker is composed of a electrical device, a battery, and leading wires. And as we know, a magnetic field that's imposed by an electric current can be altered by another magnetic field or another electric current due to electric field. So with a pacemaker, a lot of people with a lot of older models beyond the 2009 Medtronic model, they had to be very, very careful with electronic devices that can possibly alter the electric field of their pacemaker. A lot of the times, even something as trivial as a phone cannot be more than 6 inches close to the pacemaker, or else there was a very real danger of the tachyarrhythmial mode to be turned on and off when it didn't need to be. Even doctors would recommend patients with pacemakers would have a list of things to not do with their cell phone, so they were not able to have it like in a shirt pocket. They are not able to dial a number in front of the body. It has to be to the side. They also could not call on the same side as the pacemaker. They had to put it on the other ear. And also transcutaneous electrical nerve stimulation, so therapy that's used on top of the skin for athletes mostly, where they stimulate the skin to get a galvanic skin reaction to contract and release and to like soothe the muscles, but because it is run by electrical currents running through the body, it can alter the magnetic field, which that can then alter the performance of the pacemaker. And then, okay, so with pacemakers, we're going to be going into the physics principles of pacemakers. We're going to be going into the electric potential for conductors. To find electric potential, since it's symbolized by V, we can find it by using the dielectric constant, K, times Q, the charge, over R, the radius. Capacitance is the polarization of dielectric results in a lower electric field within it. So a new field is given by dividing the original field by the dielectric constant. So whatever you find to be the electric field, E, which is E naught over K, you would find the capacitance by finding that E multiplied by A divided by D times the dielectric constant. We're also going to be looking over resistance, which is the ratio of potential difference to the current in the conductor, using Ohm's law, V equals IR, which then can be derived to R equals V over I. The resistance of the material, or how much it can prevent currents to go through the material, can be found by resistivity, or symbolized by rho, multiplied by the length of the material divided by the area.
The first key concept used in pacemakers is voltage, which is going to be running in the battery to actually deliver the electric current needed to stimulate the heart. So in a definition, voltage is the push that causes electrons to move in a circuit. So we know many things in nature go from a high to a lowered state. The same is true for voltage, goes from a high potential to a low potential, and that gradient is going to be pushing the electrons through the wire into the nodes that are going to stimulate the heart. So in pacemakers and in physics in general, voltage is measured in volts, which is given by a V. Specifically for pacemakers, because we're working on a very specific and smaller scale, we're going to be using millivolts. And again, it is in the battery, so it's going to be providing that push for electrons. And it's referred as amplitude or pulse amplitude. And that's referring to the push that the heart gives. And that's going to be very important in the pacemaker's ability to sense that push, the amount of voltage each heartbeat delivers, so that it can deliver an appropriate electrical signal to stabilize it and return it back to normal. So key concept again is Ohm's law, as Helen said. So it's a fundamental principle describing the relationship between voltage, current, resistance. In its simple form, V equals IR. Voltage is equal to the current times resistance, which can be derived to R equals V over I. So looking at it, playing with the proportions, if we reduce the voltage by half, then we are going to be also cutting the current in half, because there is a direct relationship in this derivation. When we reduce the resistance here in half, we're going to be doubling the current because of the inverse relationship, and likewise, increasing resistance will decrease the current if we were to keep voltage constant. So we're going to be using these amounts to find the amount of current necessary to deliver through each heartbeat. We already talked a little bit about resistance in Ohm's formula, in the Ohm's law, but just to go a little bit more in depth. High resistance reduces battery current, so as we saw, a higher resistance is going to decrease current, and that increases longevity of the pacemaker. In pacemakers, it's very important to consider longevity because it is an internal device. So, having it function for as long as possible means decreasing the amounts of time surgeons have to, go in and replace the battery of the pacemaker. So a good way to increase longevity is increasing resistance to decrease the current. On the other spectrum, we have low resistance is going to allow more current to flow through, and because you have a lot more current going, you're going to be decreasing the longevity. You're going to be draining the battery more. One of the things that can go wrong is insulation breaks. So because this is in the body cavity, there's going to be these interactions of fluids, but pacemakers have an insulation to kind of protect from that. When the insulation does break, we're exposing the wire to body fluids, and we're causing the resistance to decrease up to a point of less than 300 ohms. Once we get to that point, current is going to drain faster and faster and faster, and the battery will deplete as well. Okay, so sensitivity of voltage. Sensing means that pacemakers monitor their heart's natural electric activity and can sense when a normal heartbeat is. So depending on the heart's voltage that it's pumping out, that pacemaker will know whether that's normal or not. The way it's going to know if it's normal or not, it's going to be, so again, it indicates the minimum intracardiac signal sensed by the pacemaker to initiate whether it should respond or not. And this is extremely important in the newer pacemakers where fluctuation in activity causes an equal fluctuation in the pacemaker's signaling. So here's a better model. So when we raise the sensitivity number, we're giving it a higher threshold of voltage. So the point at which it fires, the voltage at which it fires is going to have to be bigger and bigger and bigger until it reaches. So for example, the highest one we have here is 5 millivolts. If the heart is pumping at 1 millivolt or 2 millivolts, it will not fire. On the other spectrum, if we have a low sensitivity of 1 millivolts, it will fire at the 2 millivolts and 5 millivolts even though there is no real need. It might just be due to increased activity. So you can see how this would be a very big problem with older pacemakers where they would just fire at a set rate. Here, by fluctuating the sensitivity, we're accommodating to the person's actual heart rate at the moment. So undersensitive pacemaker will cause it to overpace. It will be firing that signal more and more rapidly because the low sensitivity is reached quickly. And the same is for oversensing will underpace. Okay, one of the last ones we're going to be looking at is capacitance. And again, it's used in this newer pacemakers of demand pacing. So when the heart is beating normally, the capacitor in the pacemaker does not charge because, as we said in the previous slide, that maximum threshold has not been reached yet. When it does, or when the heart skips a beat, the capacitor in the pacemaker fully charges. And we know that once it does, it will release its stored energy through the lead wire and into the heart to create that correct heartbeat. Once a certain potential is reached, which is, again, the threshold potential from the heart, then the pulse will fire. So, okay, so now that we talked about capacitance in the previous slide and how the charge that it stores can determine whether it fires that electrical signal or not, we're going to be applying that same concept in this problem. So a pacemaker sends a pulse to a patient's heart every time the capacitor in the pacemaker charges to a voltage of 0.32 volts. So that 0.42 volts, just to mention again, is the threshold. So at that given voltage that the heart produces, it knows to fire a signal to rebalance the heart back to its regular rhythm. Moving on, it is desired that the patient receive 67 pulses per minute. Given that the capacitance of the pacemaker is 110 microfarads and that the battery has a voltage of 9 volts, what value should the resistance have? So in this problem, we're going to be using the formula that relates voltage to the time constant to find our resistance. So here's the problem. We see the 67 pulses per minute. Pacemakers work in time set of seconds, so we're going to be converting that. So we're just going to be doing 60 seconds divided by the 76 pulses per minute to get a value of 0.8955 pulses per second. We're also given that the 0.32 volts is the threshold. Our capacitance is 110 microfarads, and then the 9 volt battery. So this is the formula we'll be using. So here we plug in the 32 threshold voltage, the 9 volts of the battery, 1 minus 0.8599 seconds over the time constant, which is going to be equal to RC. So solving the problem, we're going to be dividing by 9 to get this value here. We subtract the 1 to get this value here. And then, because we want to isolate this exponent, we're going to be taking the ln of this value that we figured out, this 0.9644, and that's going to be giving us another value that when we solve for just the time constant, we're going to get 24.136. So here, given by this formula, T is equal to RC. When we divide by C, we're canceling those out, and we're getting a time constant over capacitance gives us the resistance that we need. So, just doing that, the 24.136 divided by the 110 microfarads is going to be giving us a resistance of 225 e to the 3 ohms resistor. So a resistor of this magnitude is going to be needed to accurately deliver this, this amount of charge given reaching the 32 voltage potential threshold. In a pacemaker, we utilize various properties in physics ranging from Ohm's law to capacitance. So that is our presentation on pacemakers. Thank you very much.